Let's look at some more integrals. Lots of times we figure out that the integration process is no different from what we've been doing all along. It's just that we might see a base in an integrand that reminds us of something we're currently studying and think we have to apply a new technique. But here's some examples that really utilize old techniques. So we have the first problem, the integral dx over e to the x plus 1. Now, of course, this doesn't admit to any nice substitution, and you might think, well, could I use some miscellaneous substitution? And that probably is not the best way to go. So we can look at this like a trigonometric integrand where we multiply and divide by a convenient one. What I wrote here is a convenient factor of 1. That's what we do when we use the conjugate method. So here's something to try, that is multiply and divide by e to the negative x and see if we can convert this into a substitution problem. Well, when you multiply, you get e to the negative x in the numerator, and downstairs you'll just get a 1 plus e to the negative x. But that's really good because now the derivative of 1 plus e to the negative x is the negative of e to the negative x. And so what we can do is rig this for substitution. So we don't have the negative, so we put in the negative and pay for it. And so we've got 1 over u du basically. So that's the log form. So this gives us the negative of the natural log of 1 plus e to the negative x plus c, and that's fine. That's an antiderivative, and you can stop there. But sometimes, just like the last problem, it's good to practice to see if you can rig another form. Again, it's not required, but say you're taking a test and this is not one of the possibilities. And then you got to see, okay, which one of these is equivalent to the one that I've just computed. And so what we can do at this point is just write this as a fraction, that is factor the e to the minus x, and that'll give us an e to the x plus 1 upstairs, and of course the e to the minus x comes downstairs and gives us e to the x. And so you're thinking, okay, that's an improvement. And then we can run the negative up here to reciprocate using the power rule. And then at this point, we can apply the quotient rule. So this will be log of e to the x minus log of e to the x plus 1 plus an arbitrary constant. But of course, these are inverse functions, so that's just x. And then we get x minus the natural log of e to the x plus 1 plus c. So that's just an additional amount of manipulation. Again, functions who possess the same derivative differ by a constant, but it's somewhat difficult to look at this and look at this and see that they're equivalent in terms of an antiderivative. Okay, the next one is a definite integral, and we need to always remember the fundamental theorem of calculus to compute those. And so again, this utilizes a technique that we've done many times. So when we look at this, we're thinking, okay, well, 2 plus ln of x has a derivative 1 over x, so we can kind of rewrite this in a very nice suggestive way. And of course, there's no adjustment to be made. Here's the u, there's the du. So this is add 1 divided by the new power. So the new power will be 2 divided by 2 and evaluate between e and 1. Okay, when we substitute e, go ahead and factor the 1/2 just to get it out of the way. So we have 2 plus ln of e quantity squared minus, and substituting the 1, 2 plus ln of 1 quantity squared. Okay, of course, the ln of e is 1, so that'll give us a 3 squared, and the ln of 1 is 0, and that'll give us a 2 squared. And so 9 minus 4 is 5, and divide by 2, and we get an answer of 5/2. And we are done.